Hello and welcome to Ehlanzeni College TVET Clinic. My name is C. Tobejane and today we'll be looking at Engineering Science N3 under the topic of heat. Now, if you may remember on our previous lessons, we were dealing with the specific heat capacities of a particular substance. We said that specific heat capacity does not include fuel substances, but it only includes non-fuel substances like steel, aluminum, gold, silver, metal, iron, and water. We also looked at how the temperature change is occurring in that particular element. We said that specific heat capacity is the amount of heat energy required to raise the temperature of a substance. We also went further to look at a calorific value, also known as the heat value. Now we know that calorific value is the amount of heat energy required to completely burn fuel. In this case, we have two types of fuels. We have liquid fuels and we have solid fuels. So the amount of energy which is required to completely burn that particular amount of fuel is called the calorific value. We also look at the coefficient of linear expansion, which is the amount of heat energy required to change the length of a particular object. Now, if that object it's a wire or an iron rod, and that iron rod is exposed to heat, how much heat energy should be applied to that particular rod will then determine the change in the length of that particular rod. Lastly, we look at the coefficient of area expansion. We said coefficient of area expansion is still the same. That is the energy required to change the area of that particular material. It means that the coefficient of area expansion is 2 times that of linear expansion. If you take a square plate, for an example, and expose it to heat, each side of the square plate will change in length, meaning that the total sides will then give us a new area, which is then called the superficial area. In today's lesson, we are going to be looking at steam. We know that when we're dealing with steam, in most cases, steam is produced in boiling water or when a certain particular object is being heated. Now, let us look at our screen here. We said that steam is water in a gas phase. This may occur due to evaporation or due to boiling, where heat is applied until water reaches the enthalpy of evaporation. Remember, we spoke of specific heat capacity. So when you boil water, the water will reach a boiling point of 100 degrees Celsius. At that boiling point, the water will start evaporating. Now that evaporation is called steam. Remember, we can extract steam. In most cases, steam is used in power stations to generate electricity. It is taken through steam turbines, where the steam is required to turn those steam turbines, where in turn it rotates the generators in order for electricity to be obtained. So steam is water actually in a gas phase. And they're saying this occurs due to evaporation or due to boiling of water. But then what is enthalpy? When we speak of enthalpy here, we are speaking of a thermodynamic quantity equivalent to the total heat content of a system. It is equal to the internal energy of a system plus the product of pressure and volume. So enthalpy, we're actually looking at how much heat or steam is produced in terms of volume, and that steam will be equivalent to the amount of heat that is in turn producing it, and the volume, which is the amount that is particularly absorbed. But steam has advantages and disadvantages. It means that it has its good and bad part. Now, the advantages of steam is that steam can be used repeatedly. What's nice about steam is that it never gets dirty. It can be used over and over and over. It cleans itself. Coal and water is reasonably cheap and readily available. Remember, in power station, we need coal in order for us to produce steam, right? So which means that the coal will be required to burn the water, to boil the water. such that steam is produced. So these two components are easy to find, which is the good part of it. Low-grade fuel can be used to keep the cost low. It doesn't matter the kind of fuel that we use. As long as it produces heat for our water to boil, then we know that we can then spend less on that. Steam installation has long life. Unlike water, which can cause rust, steam cannot cause rust. So this installation, the machines which uses steam, can last for a very long time, and we cannot have rust occurring in that nature. But then let us look at the disadvantages again of steam. When we talk about the disadvantages of steam, they say here steam layout must be erected where water and coal is available. This means that we cannot erect steam structures or boilers where water and coal is rare to find. This means that it has to include a lot of transportation of the steam, and we don't wanna anchor so much cost. We need to cut cost as much as possible. So we cannot just build those structures anywhere. That is a disadvantage, because we cannot just erect them anywhere. So we need to erect those structures where water and coal is close and available. Water is lost due to evaporation. You see, now in South Africa we are having a crisis of droughts. We are entering a phase where the amount of water in our dams, in our lakes, they are burning out, it's evaporating. So the more water we use, it means that we are losing that water to evaporation. The initial cost of installation is very expensive. Remember, we said that those structures can stay for the longest time. But to erect them now, that is the expensive part. Because normally when you erect a structure that is going to stand permanently, that structure will be very costly. As a result of the combustion, the atmosphere is contaminated. We are burning coal, which is fuel. When we burn that fuel, the fuel produces certain elements. The combustion of those elements, they travel to the atmosphere, which in turn damages our atmosphere. So these are the disadvantages of steam. I hope you are paying attention to those. Now when the water or when the form of water changes, it travels through different stages. Ice changes to water, and then water is then now heated, which changes to steam. This means that that process has a certain amount of stages that needs to be looked at, and in that case we use that to read those stages by making use of a temperature enthalpy diagram, as you can see on your screen. Now with our temperature enthalpy diagram, if you can look at point A and B, we are having ice at negative 20 degrees Celsius. Before that, we have our y and x-axis of the diagram. The y represents the temperature change. The y-axis represents the phase change: ice, water, steam. A and B represents what? The phase of ice. A and B represent ice. But as you can see there, what we're having is that ice needs to change in temperature before it starts melting. We cannot have a situation where the ice will just start melting without any change in temperature. The temperature has to increase from negative 20, as you can see in the structure, to at least 0 degrees Celsius. Then the ice is ready to melt. So that heat responsible in changing the temperature of that particular ice is called sensible heat. Now, sensible heat is responsible in changing the temperature of ice, right? So our ice has changed from negative 20 to 0 degrees Celsius. It means at that point, now we need to apply a certain type of heat for it to change its phase. Now, still at 0 degrees Celsius, A, B to C, we are applying what we call latent heat. Now latent heat is that heat responsible in changing the phase from ice to water. Now as you can see on the y-axis, now the ice is changing to water. But check the temperature, it does not change, which means that the temperature remains constant, 0 degrees Celsius. And then going to point C and D, this is the point that we want the most, where we now have water. Remember, our main aim is to produce steam. So for us to produce steam, we are going to use ice, which is easier to transport. From point C to point D, we are now changing again the temperature of water. The boiling point of water is 100 degrees Celsius. This means that water can never evaporate or boil before it reaches 100 degrees Celsius. So that part is where we are now increasing the temperature of water, and it is called HF, because now the temperature is going from 0 to 100 degrees Celsius, and 100 degrees Celsius is called the superheated temperature. Now we are now starting with our heat enthalpy. Now let us look at point D to point E. Point D to point E, our temperature remains constant, 100 degrees Celsius. But what is happening to the water? The amount of water decreases. As you can see, we have a dryness fraction line showing that the water decreases, changing to steam as steam increases, right? So if we have 15 cubic meters of water in terms of volume, then now the water decreases with the increase in steam. Now that is called HFG, because now we are now changing the phase of the water from water to steam. Point E to point F, we are again applying sensible heat. We no longer have water, but we have steam now available, which means that we are now increasing the temperature of steam to a superheated temperature, and that is called enthalpy of superheated steam. This table, folks, in figure 5.3 represents the phase change of water from ice to steam with the phase change, or rather with the change in temperature. Now with that, we have important equations that we need to understand, especially when we are dealing with this steam. These equations are called enthalpy equations. If you can look at your screen, we have important formulas. We have the first one in 5.13. It's called the enthalpy of wet vapor. Remember, when we first produced our vapor or our steam, it's wet, such that if you have a pot and you have boiling water and you put your hand just at the top, you'll see your hand getting wet. That is called wet vapor. And the equation to calculate the amount of wet vapor is given as HW is equal to HF plus XHFG. What is X? X represents the dryness fraction. That wet vapor, what amount of dryness fraction factor does it require for it to dry out? HF, we did speak of that, but we are going to look at a table that will clearly indicate what HF is and the values of HF and HFG. 5.14, we have the enthalpy of dry saturated vapor, Hg. Now, the vapor is drying out, right? So that liquid enthalpy is called HF plus the enthalpy of evaporation of dry vapor, HFG. So it's given as Hg is equal to HF plus HFG. We again have the enthalpy of superheated vapor. Remember, now we are superheating our vapor. The enthalpy of superheated vapor needs a specific heat capacity of vapor, of steam. So we need the specific heat capacity of steam for us to understand that. So that is given as H sup is equal to, or H superheated is equal to Hg plus Cp into T sup minus Ts. T sup meaning the superheated temperature, Ts the saturation temperature. That is 5.15. And then in addition, we have the amount of enthalpy of evaporation required to dry the wet vapor. Now we have wet vapor and we need to dry it out. That equation is given as H1 minus X is equal to HFG 1 minus X. These are the equations that you must understand and know how to use them. Remember, when you get into an exam room, you'll be given a formula sheet. In that formula sheet, you will be able to detect these equations. But at the same time, you need to request to be given a book called the Properties of Steam table. In that book, that is when you are going to get the value of your saturation temperature Ts, the value of your HF, the value of your Hg, the value of your HFG, as well as pressure. The question in an exam will give you a certain amount of pressure, and then when you go to that book, following the pressure line, you'll be able to detect such information. Now inside that book, this is what you have to see. Properties of steam, which is called a steam book. Look at the first line. We are given 600 kilopascal. 600 kilopascal, our Ts, which is our saturation temperature, is 158.8 degrees Celsius. Forget about Vg, go to HF, 670, you take that value. HFG, 2085, you take that value. Hg, 2755, you take that value. You forget about SF and SG, it does not fall under your scope. So each time you're given such a question, this is what you need to look at. Now let us see if we can apply the information that we've acquired today in an exercise. If we are able to apply that, then we'll be able to detect what is it that's needed. We have our exercise there. If you can look at our exercise, 5.3.2 and 5.3.3. Taken the liberty of including the question, or rather the formulas at the side. Let us look at the first question. They say water at a temperature of 23 degrees Celsius is fed to a steam boiler. The boiler pressure is 760 kilopascal and the dryness fraction of the steam is 0.85. The steam is now heated to superheated steam with a temperature of 230 degrees Celsius. That is our superheated temperature. Now, we need to extract our data in this case. Let us transfer our equation here to a place where we can write well. What is it that we have? Let us look at what we have here. We have our initial temperature, right? They say the water had a temperature of 23 degrees Celsius. Let me use a different color here. 23 degrees Celsius. That is what we have, right? 23 degrees Celsius. They say the water is fed into a steam boiler. The boiler produces, or the boiler pressure is 760 kilopascal. Remember our steam book. This is where now you go and check your steam book. And they say the dryness fraction is 0.8. The steam is now heated to superheat steam with a temperature of 230 degrees Celsius. 230 degrees Celsius. Let us extract our data before we start with everything. Let us extract our data. Let's use a black color here. Let us extract our data. So what is it that we are given here? We are given initial temperature. We are given Ts, the temperature of water, which is 23 degrees Celsius. We are given pressure, which is 760 kilopascal. We are also given the dryness fraction, which is 0.85, and we are given the superheated temperature, which is 230 degrees Celsius. Now let us quickly look at this. When now we are having 760, what is our saturation temperature? Saturation temperature is 168. Let's write that. TS 168 degrees Celsius. It's 168. Let's look at that carefully. 168.3. HF at that line. HF at that line is 712. HF is 712 kilojoules per kg degrees Celsius. We are looking for Hg and HFG. We need this information so that it can be easier for us to start calculating. 712, 2054. So our HFG is 2054 kilojoules per kg degrees Celsius. And then what is Hg? 760. What is Hg? 2766. Our Hg is 2766 kilojoules per kg degrees Celsius. That is what we have now. Let us now quickly try and answer our questions. Number A, they want us to calculate the enthalpy required to change the feed water from 23 degrees Celsius to wet steam, right? To wet steam. So, which means that we are saying HW, we need that wet steam, is equal to HF plus XHFG. It's the first equation there. It's the first equation there. So we have our HF, in this case, HF is 712 plus our X is 0.85 multiplied by our HFG, which is 2054. Folks, have your calculator handy? I hope and believe you are able to use your calculator. You've been trained in mathematics on how to use your calculator from N1 and N2. There's also a chapter in mathematics N3 that shows you how to use your Casio calculator. So kindly please learn how to use your Casio calculator. It is of paramount importance for you to know how to use that. So when punch that in our calculator, what we are getting here is 2457.9 kilojoules per kg degrees Celsius. Remember the SI unit, kilojoules per kg degrees Celsius. That is our first answer. Number B, they want us to calculate the enthalpy required to produce the superheated steam from the wet vapor. So we are now calculating H superheated. We are now calculating our superheated steam, which is given as, this is the second equation. This is the second equation, Hg plus Cp into T sup minus Ts. Remember, your specific heat capacity, you are going to obtain your specific heat capacity in a question paper in a table of properties. There's a normally you'll get a document in your question paper where it contains all the properties and heat values. So that is where you are going to get your steam, your specific heat capacity of steam, right? Your specific heat capacity of steam. That is where you are going to obtain your specific heat capacity of steam. You use that specific heat capacity of steam and you substitute it here, right? In this case, what I will do, I will use the specific heat capacity of water, because in this case, I don't have the question paper before me to refer where I will get the specific heat capacity of steam. But when you have the question paper, you go and look at the capacity of steam, the specific heat capacity of steam. You extract that value and you substitute it here. So here our Hg is given as 2766 plus our specific heat capacity of steam. I'm going to use 4.2 kilojoules per kg degrees Celsius. our 230 degrees Celsius, that is our superheated temperature, and our saturation temperature, in this case TS, is 168.3. 168.3. Punch that in your calculator. 2766 plus 4.2 into 230 minus 168.3. 168.3, and I'm getting 3025.14 kilojoules per kg degrees Celsius. Kilojoules per kg degrees Celsius. Now, looking at the last equation, the total enthalpy required to produce superheated steam from the heat. Now, the total enthalpy required to produce now that superheated steam, right? So, which enthalpy is required to produce that superheated steam? Is the enthalpy of drying the wet vapor, right? We are drying the wet vapor. That is the enthalpy of drying the wet vapor. HFG in our case is 2054 into 1 minus 0.85. We are drying that wet vapor there, and that enthalpy is 308.1 kilojoules per kg degrees Celsius. Per kg degrees Celsius. Now, please, I want you to take note of this. Take note of this. You are given HW is equal to HF plus XHFG. This is because now we are looking at 1 kg of steam, right? We are looking at 1 kg of steam. But if we have more than 1 kg, which means that in the statement they give you the mass of the steam to be 2 and above, it means that this equation is going to be multiplied by m, right? This equation also, it's going to be multiplied by m. All our equations, all these equations will be multiplied by m. All these equations will be multiplied by m. Did you get that? Perfect. I hope you understood everything in the lesson. I'm leaving out 5.3.3 for you to do at home. You can copy that and then you try it out. On our next lesson, we are going to be looking at a different chapter. I hope today's lesson was fun and exciting. This is Sito Bejane from Enthalpy College TVET Clinic. Hope you check us out on our social media platform. Till we meet.